Hello, hello, hello. All right. There's all right. It's the double. It's the Lila. It's the Mancha. It is awesome. It is all happening. It's the Sophia. It's the hat trick. I mean, the three some. That's awesome. Sophia, Mancha, Lila, Raymond, four. You guys set records. I'm telling you, I'm not comparing one class to another, but I'm totally am comparing one class to another. The middle of the day. Maybe it's a time of day thing, but you guys do a lot more. Oh, and there's Michael. There's like more video that I feel like we should be a TV show. All right, awesome. I'm so psyched. Hello, everybody. It does mean a lot, honestly. All right. So there's who else? And Fatima has the avatar going, like at least the color going, which is certainly helpful on a dreary day. And everybody's coming in. Okay, okay, okay. Oh my God, there's chopsticks involved. Okay. Um, wait, I'm trying to figure out, is the Mancha Raymond situation the same are they both in the same place again as, oh, it doesn't matter. It's none of my business, but no, that's not the case. Okay. Good afternoon, Camille. Thank you. Oh, a lot of people. Okay, 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 okay. Good afternoon, Samia. Oh, God, I'm sorry, I missed all of this. Good afternoon, Jerry. Good afternoon, Luis. Good afternoon, Samaya. Good, uh, everything is good. Thank you, Nico. How's everything with you? If you answer, you get points. Good afternoon, Camille. Good afternoon, Leah. 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 Sorry. Doing well. Thank you, Mancha. Faking it well. Anyway, fake it till you make it. I'm saying, good afternoon. Thank you. Oh, I see. It's craft. I mean, see, doesn't video make such a difference? All right, video killed the radio star. Whatever. No, I'm doing fine. Thank you. I mean, do we have time for the truth? No. Hi. Oh, and Montserrat. Hi. Awesome. Um, yes. Yes. Okay. No, I know Montserrat has a thing of finding another professor. I'm working on that other professor, Montserrat. I mean, well, anyway, you know. Anyway. Okay, 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 okay. So we should start. What did I forget? I think I've said hello to everybody. Okay. So what I want to get back to is this business of electrostatics of the fundamental interactions. Hello, let's go. Why is there so much delay? That, yes, I want to get back to that business. Um, Specifically, though, even though I just waited for this uh, screen share to come to life, I actually want to switch the screens and show you what we're specifically. Okay, so yesterday I started introducing the electrostatic force, i.e., the electrostatic interaction between any 2 point charges. Yes, that's right. And the sort of summary or takeaway of yesterday, Monday, is that any and every bit of electrical charge in the universe automatically pulls or pushes on every other point of charge in the universe in a manner that is mathematically identical, or mathematically similar to the manner in which every single bit of mass in the universe pulls on any and every other bit of mass in the universe, right? I mean, that's the quick summary of yesterday. In other words, both of these interactions, these forces, the gravitational force, the electrostatic force, they're both fundamental in the sense that they just happen automatically without any activity having to bring them into effect, right? As long as a mass exists over here, and as long as a bit of mass exists over there, then each mass will just automatically pull on the other mass, whether there's empty space between the two of them or whether there's matter in between the two of them, no matter what, whether each one is sitting still or each one happens to be moving, every bit of mass automatically pulls on every other bit of mass in the universe all the time. I'm saying that slowly and I'm saying it emphatically, not because I think that is obvious. I mean, it may seem obvious because you might have heard it before, but when I emphasize that point, what I'm not trying to say is, oh, we all proved that, or oh, doesn't that obviously make sense? Like, not at all. I'm not at all saying that it makes sense, not yet. I'm saying it's true because it evidently, apparently, scientifically, experimentally seems to be true. Would I have thought that it was true? No. Uh, If I didn't look at the evidence or look at the evidence that other people have looked at before me, right? But it apparently is true that every bit of mass can pull on, does all the time pull on every other bit of mass without touching it. Like, that's really what I'm trying to say in the end of the day is that bits of mass, whether it's the center of the sun and the center of the earth, or the center of the earth and the center of the moon, or the center of the earth and a brick falling, or like a rock falling toward the surface of the earth, evidently, this pull that we call gravitation, which exists universally, evidently, it doesn't require material contact in order for it to occur. And similarly, the electrostatic interaction between protons or protons and electrons and electrons, that electrostatic interaction is the same qualitatively, conceptually, in that evidently a proton doesn't need to touch an electron in order to pull the electron toward it. The electron doesn't even need to be nearby the proton in order for the proton to pull it. And furthermore, even if you try to block this phenomenon, I mean, this is the same thing with gravity that I'm saying. If you try to block the phenomenon by putting like cotton or carbon or gold or whatever, or water between the proton and electron, it doesn't matter. You can't help the electrostatic interaction, the electrostatic force, the electrostatic pull or push. You can't help it with any kind of thingy material, and you can't stop it with any kind of thingy material. I mean, you could stop the effects, don't get me wrong. I mean, just like you could put a table underneath like a coffee cup so the coffee cup doesn't end up on the ground. But you're not blocking gravity when you do that. Let's just be clear, right? Any more than if you put cotton between a proton and an electron, you might stop the proton from getting, or you might stop the electron from accelerating toward the proton. But you're not blocking the force you're just introducing another force. And the net force then is zero. I mean, I'm getting away from myself, but like, so in other words, the gravitational interaction and the electrostatic interaction, they don't require any kind of material medium to transmit, or evidently, they don't require any kind of material to transmit this interaction. That's why the gravitational interaction, and interaction is just a synonym for force. So the gravitational force and the electrostatic force are both the same in this respect, in that they are action at a distance, like they occur over distances, any distances. And furthermore, and I think I just saw out of the corner of my eye that something happened in the chat, which is almost exciting. I'm almost glad. Give me 1 second. So on the one hand, qualitative. So we're here to study electricity, but everything I say about electricity is based on whatever we already kind of believe or observe about gravity. Like the concept is the same, and it's kind of easier to picture with gravity a lot of the time. But then also my big point that we have to use for problem solving and so forth is that the mathematics end up being the same. One of the really interesting features of the universe or physics is that interactions that are fundamental in this way tend to be expressed by equations that have an r squared in the denominator. Interactions that are fundamental, interactions that occur through empty space without touching, seem to be inversely proportional to the square of the distance between the two objects. That's very interesting. Can I ultimately explain why that is? Yes, ultimately, you're going to see that after you solve enough problems and expand enough. But at first, but it's almost a curiosity that maybe, at least for me, motivates me to want to solve certain problems and unpack the equations, because it is a very interesting discovery or realization that if two things pull on each other through empty space, they're necessarily going to do it in this mathematical way of inverse r squared proportionality. Okay, so that's the summary from Monday. We're going to now start practicing the equation for the electrostatic interaction, the electrostatic force, the Coulomb force. That's what we're going to start practicing in a minute with a screen share that I'll switch. But first, I think there's something in the chat. Sorry. Oh, no problem. Oh, no problem. Okay. Okay. So I'm going to do a quick screen shift here, because what we're going to go over, what we're going to start talking about now is something that many of you courageously and responsibly already tried to do and hand in, which I appreciate. But we're going to walk through, but some of you have not, and I'm going to use it. And for those of you who did hand it in, you may well want to find out whether you did it right or not or whatever. So we're going to start talking. So everything I just said, right, and everything I said Monday is kind of summarized right here. So what this is homework number. I don't even remember now. Someone can remind me. Homework number 6. I think it's 6. Yeah. It's right here. These equations summarize everything I just said a minute ago. But let me actually, as long as I'm doing this, I want you to correct something on your side. This is a PDF. I can't like do this in real time right in front of you, but I would strongly urge that on that gravitational equation right there in the center of the screen right now, add a negative sign to that, please, like right before the GMM business. Put a negative sign in the equation. It's literally a mistake that it's not there. It's kind of a big mistake that it's not there. So yes, thank you. And I totally see that. See, this is the power of video. I totally see that Lila's doing it. That Mancha, I think, just did it, or Sophia's totally doing it with chopsticks. I'm just kidding. And then the second equation. Oh, he's got the. Oh my God, he's got the chopstick. Or is it a pen or chop? That. Oh my God. Wait, that's really weird. Why did I just? Okay, thank you, Michael. That, and see, this is participation. There should be a portal just for like showing chopsticks when the professor mentions it. Um, Sorry. Yeah, I know why you guys do. I know. Yeah, the reason that people don't participate when they don't is that they're afraid they're going to throw me off for like 20 minutes from the topic. And you're probably right. Okay, sorry. But the other correction is, yes, put in a negative sign in the first equation, but then in the second equation, take out that plus or minus. I know why it's there. I understand, but it's actually confusing that it's there. On your side, please, like, yeah, put a negative on the first equation, take out the plus or minus. I'll quickly say why or what the deal is. What I think we said yesterday, what I know we said Monday, is that if you take the unit vector notation seriously, if you take seriously this idea of r hat, then what it allows you to do is recognize that from here on in a fundamental force equation, if you see a negative sign, that means attraction. Negative means pull. And if you see a positive sign, that means repulsion or push. Now, gravity is always a pull. It always has a negative sign there. In other words, if r hat points by convention from M1 to M2, if necessarily the vector R, the displacement vector, is assigned, is defined to be pointing from the big mass to the small mass, then the force that the big mass exerts on the small mass takes that displacement vector and flips it around so that the force of the gravitational force exerted by M1 on M2 always points back toward M1. M1 reaches out and grabs M2, pulling toward it. That's a pull. That's an attraction. And that's what the negative sign means. It means back toward the original object that's generating the force, right? Okay, so there's always a negative sign on the gravity equation because both of the masses are always going to be positive. But then on the electrostatic equation, the Coulomb law underneath it, the reason there's a plus or minus there is it could end up being plus or minus, but really you don't have to put the plus or minus there. The plus and the minus gets taken care of automatically by the signs of Q1 and Q2. Q1 and Q2 are the 2 point charges, right? And they could be either protons or electrons. They could be positive charges or negative charges. So so Q1 and Q2 already have their own signs. They might be negative, they might be positive. And the combination of the two signs will determine what the final sign on the equation is. Meaning, oh my God, Abdul, wow, that's amazing. Okay. The final sign on the equation for the electrostatic equation is determined by the combination of the two charge signs. Meaning if they're both positive, if Q1 and Q2 are both positive, then a positive times a positive equals a positive. You get a positive on the whole thing. If they're both negative, a negative times a negative is a positive. You get a positive on the whole thing. And doesn't that make sense? Because we're saying positive means push, negative means pull, attraction, positive means push, repulsion. So if both the signs are the same, we get a push, which you already know from chemistry and everything like that. If they're both electrons or they're both protons, they're going to push each other away, like in the direction of the R vector. But if they're opposite signs, negative times a positive or positive times negative, you get a negative, so it'll be a pull. That's how this all works out nicely in it. All right, anyway, so correct those two, thank you. And then it gives the numbers, which we referred to yesterday. So it gives all the facts that we referred to Monday. Okay. That's what the homework does. Then it starts asking you this problem, which is sort of a plug and chug exercise in a way, or it starts off as a plug and chug exercise, but then it gets very exercisey and it seems to get very repetitive. Like it asks you one plug and chug question and then it asks you basically the same question 4 more times. And it seems like annoying and repetition, but it's for a reason. So I want to show you, I want to go over it right now. So again, what I'm doing is literally walking through this homework sheet right now. I'm not doing the 5-step method right now. I'm just trying to do the physics and show you like my point. So I'm basically also just trying to show you what the right answers are. So again, if you've already done this homework, but you got the wrong answers, obviously you could feel free to use this, what I'm about to do, to correct and re-upload and get all the points. Or if you haven't done it yet, yes, you can benefit from this, but you have to do the 5-step method and like show, you get my point. All right. So you can't just like copy this. All right. Anyway, so we're going to switch. So this is what we're doing. I'm going to switch the screen. Sorry, I'm just. Yeah. Okay. So I'm going to switch the screen and solve this problem. Oh, no, I'm not. I think it's homework 6. Correct me in the chat if I'm on the wrong. I think it's homework number 6, but you can tell me. Um, okay, sorry. So this is a setup, right? We've got a big charge, point charge over here, plus 50 coulombs, then separated by a distance of 5 meters. We have another smaller charge Q2 over here, and in the first and in the first exercise, the second charge Q2 has a magnitude of plus 3 coulombs. Couple things to notice. Well, you notice the pattern of the problem, like what stays fixed in this problem. So you imagine you're like in a lab, and there's this big amount of positive charge over here in the lab. Like it's a point charge, so that means it's like over 100 quintillion protons all jammed together into this tiny, tiny space. They're all protons, they're all positive. So it's so many, like if you had 16 quintillion of them, it would make 1 coulomb of charge, but we have 50 coulombs of charge. So we have 50 times 16 quintillion little protons all jammed together in a tiny space over here. So it's like a really charged up dot over here. And then 5 meters away in a particular direction, we have this other little charge, like a lot fewer protons jammed together to make the equivalent of like 3 coulombs of charge. Okay. And the first goal here is to figure out how hard, how many newtons of force, with how many newtons of force does this 50 coulomb charge push on the 3 coulomb charge? Like that's what we're going to figure out right now. And yes, in a way, it's just a plug and chug. But notice, before we go any further, notice the pattern of this problem. Like exercise one, the Q2 is plus 3 coulombs. And then for every exercise after that, they don't change anything in the problem. They just swap out the magnitude of the Q2 and they just replace it with different possible values. Okay, so you're picturing that you're in the lab. What you're really trying to do is sort of see what the effect of this big charge over here at this distance is. You're trying to see what its effect is on various different receivers or receiving charges, right? So, and that's like a custom, there's like a lot of reasons to do that. So, what I want to say vocabulary wise before we go any further, traditionally, then the big Q1, the capital Q1, the one that we're considering to be creating the force or generate or exerting the force, we generally call that the source charge. And the one that's receiving it even says this in the sheet. I'm sorry, I'm spending so long. It even says this in the sheet. But yes, whatever is creating the force, in general, we call the source of the force. And whatever is receiving the force, we call the test. Because we can imagine, as in this problem, testing the effect of the source on holding everything else equal and in testing it on different possible recipients. Okay. So all that said, the first question is, what is the electrostatic force exerted by the source charge onto the test charge? So we want to know. We want to know the force okay. So we use the electrostatic interaction, the Coulomb force. This is the jjP in effect. Now we write it, you want to get in the habit of writing it in this weird way. Like the constant, we write in a strange way in the parentheses. But it is just a strange way of writing it. If we start plugging in numbers, Oh, no, so I'm just plugging in, right? I'm just plugging into the equation. Many of you have already done this, but just notice a couple of things while I'm plugging into the equation. First of all, that R hat, it doesn't change the multiplication. It's not anything that goes into my calculator. The R hat um, has a value of 1 always by definition. So it's not going to change the numbers. Second of all, just to make this easier for me to be able to do without a calculator or to get perspective on it, I can round, just like we round 9.8 to 10 meters per second squared, 8.999 times 10 to the ninth. I can round to like 9 times 10 to the ninth. That makes the math a lot easier. So if I do that, and what's in the denominator, notice it's r squared, right? So I guess what I'm trying to say is that 8.99 times 10 to the ninth is the number for that whole block in the parentheses. We write that whole block in a funny way for reasons you'll see soon. But if we're plugging numbers, it doesn't matter how we write it. That's the number. Um, so I can do this. So basically it's, oh my God. Okay. Wait, I'm sorry. I'm not changing it. I'm just going to give myself more room so you can see it more. Okay. So in the yellow is the answer. Now, again, okay, just again, it's a plug and chug, but some, God, I'm sorry. I'm so, great. What's in yellow is the answer. Um, all I did was like multiply numbers, but oh, oh, I see the chat. It is in fact homework 6. Okay, thank you. Sorry, thank you. That was like 8 minutes ago. Okay, thank you. Got something right today. Okay, that's good. All right. What's in yellow is the answer. A couple of notes about it. First of all, note that it is a positive answer. It's specifically well, even before that, it's an answer in newtons. It's a force. It's saying that this bunch of protons over here is exerting this much force, like in other words, 54 billion newtons of force onto the little protons over there. Now that's a lot of force. Is this realistic? Well, it is realistic if you actually had that much charge. That's a lot of charge to have. But charge does exert very strong forces on other charge for what it's worth. So first of all, it's saying that this bunch of protons over here is exerting that many newtons of force on this few protons over there. Second of all, it's a number in newtons times r hat. What does that mean? What it means is it is literally the force is pushing along the line that geographically connects these 2 point charges. The r hat in the answer is saying that the force, if the line, you imagine a line connecting Q1 to Q2, wherever that line is in space, the force is directed along that line, like as opposed to being perpendicular to it or something like that. Like, so, and specifically, furthermore, the fact that it has an R hat and a positive sign means literally, okay, Q1 is pushing on Q2 directly in the direction of that line, but it's toward Q2 as opposed to back from it. So it's a push, it's repulsion, not attraction. Okay, I think you understand all that. That's the answer to that one. And it's just, in the end of the day, I'm over talking it. It's just a plug and chug. But now, so that's the force that one object exerts on the other. If I were to think about Newton's third law for a moment, I would realize that the other is also directing a force on the one. Like Q2 for sure is also pushing back on Q1 with the same magnitude in the opposite direction. And that's true. That's not what the question's asking, but that's what true. So, okay, so what? Um, so what? Now we go to exercise B. It gets a little bit more interesting now. Or exercise, whatever it's exercise Roman numeral. Yeah. Now, the only thing that changes now. Okay. We're supposed to, so the only thing that changes now is now the test charge is now -6 coulombs. And now we're being asked to compute the new electrostatic force, right? So what we could certainly do is just take the new fact and plug it back into the old equation. Like we could do this plug and chug again and just get a new answer, and that'd be perfectly fine. And by the way, if you did that on your homework, that's great. Like no problem. But it might occur to us there, but it might occur to us that there might be an easier way to do this. Like I might notice that the magnitude of the electrostatic force is directly proportional to the magnitude of the test charge. I mean, it's also directly proportional to other things like the source charge, but the magnitude of the electrostatic force is directly proportional to the magnitude of the test charge. So, meaning whatever change I make to the test charge is correspondingly going to be the exact same change to the overall answer. I mean, I hope that's clear. I mean, that's what direct proportionality means. So I might say to myself, this is like annoying and boring and repetitious already. Like I already got the force on the whole thing. Instead of recalculating, I could say, look, all you changed was that you doubled the magnitude of Q2 and then you threw in a negative sign. So you, in effect, we multiplied Q2 by -2. That's all we did. So wouldn't it make sense? I think to myself, couldn't I save time and hassle by just taking my old answer and multiplying it by -2? And the answer is yes. This is not a trick. I'm actually trying to make a point here slowly. But yes, if that occurred to you at all, you are correct. And there is no, I mean, that is a good trick to do, and there's no trick against it. So, because of direct proportionality, thus, if we want to get like the new FE is just -2 times the old FE, electrostatic force. Thus, I'm saying, FE for part 2 of the problem. So that will equal 1.08 times 10 to the 11th newtons times r hat. But now in this case, it's a negative this one will be a pull, right? Um, and that's the answer for, I should put it in yellow. Sorry. That's the answer for this one. I'm, I mean, stop me if you want, but I dare you. No, I'm just saying, okay, if you really believe that the force is directly proportional to the test charge, then whatever you do to the test charge, if all other things are held the same, whatever you do to the test charge is what you do to the overall force. End of story. Okay, so that's going to help us for the rest of these exercises, right? That should save time. But then, but then I go to the next one. And now here in the next one, Q2 now equals +5. So I say to myself, can I still do this trick? Yeah, I could still do this trick. Uh, but is it as exciting or as time saving to do the trick now? Like now to do this trick, I would have to do this. Right now, in order to do this trick, I have to like multiply by 5, 6. Why? Because the other one was 6 and now it's 5. Like I could still do that. Don't get me wrong. But now it's getting a little annoying. Like now, it's almost not even clear to me that's as much of a time saver as just plugging into the freaking equation. In fact, if you're anything like me, I might do this for the sake of doing it, but then I would still feel compelled to check with the original equation that I did this right because I'd be like, is it 5/6 or is it 6/5? I can't even keep this straight. I mean, what's my point? What's my point? Is for a minute it looked like that was a good trick. Now I'm not sure if it's a great trick or not. So I keep going, however I'm going. But I mean, I do get an answer. I mean, we can get an answer. The answer is um sorry, I should, um that can't be right. 1 second. Oh, okay. I think it is. And this one again is you could check. I might have just done the math wrong, but this one again is positive, right? So I'm not sure if I'm loving the trick anymore, but I go on. And then I get to the fourth one, just when I'm sort of about to kill everybody. I get to the fourth one, and now the fourth one says, "Wait a minute, what's the force now if the test charge is 1 coulomb?" And I start to realize, oh, wait a minute. If it's 1 coulomb, like, okay, so I divide by 5 again. So I say here, I'm just, oh my God, what's going on with my board? Sorry. I don't know why my board just, hold on a second. Okay. Um, I get this one, and stop me again. I may be making a I am tired. So stop me if there's a computation error somewhere in here. But this is what I get for the answer for 1 coulomb. Like I just divided the other one by 5. Like that wasn't a bad thing to do, right? I mean, I just divided the last one by 5. But the reason I'm getting excited now is I say, oh, wait a minute. Now, when I get to the last question, like I thought this was going to get super annoying, and maybe it is getting super annoying. But the last question now, I can just now, if Q2 equals like negative 2 now just what I'm saying is, okay, I apologize for my handwriting and everything, but here's the real point I'm trying to make. By the time I get to step 4, and it asks me just get the force for a situation where the test charge is positive 1 coulomb. Once I get that and it goes to step 5 and says, okay, now do another one, that's when maybe it occurs to me, oh, I wish they had asked me that all along or right from the start. Like, if you think about it, once you get the idea that whatever change you make to the test charge is automatically the change you make to the whole force, right? Like, this is the first insight of step 2, I mean, of part 2, is once you realize that the whole force is directly proportional to the test charge, and therefore whatever change you make to the test charge, you automatically make to the whole force, then what eventually occurs to some of us is, oh, so actually, really what I need, what I'd like to get right away, what would help me in the future is once I just stop everything and just get what is the force that would be exerted on a positive 1 coulomb test charge. Then from now on, once I have one, in other words, question 4, once I have one, then from here on in, anything I do to the Q2 is easy to multiply by, right? In other words, there's no more 6/5 or 5/6 or anything like that. Now, if anybody asks me if they say the test charge is -2, or they say the test charge is +6, or they say it's +1,000,000, all I do is take my answer from 4 and multiply it. So there's something very useful mathematically and very time saving about the answer to number 4. Let me emphasize that. Okay. And I know, well, yes, I guess the sheet does say all of this, but what I'm saying is that fourth step that we did, when you find out the force that a certain source would exert on a positive 1 coulomb, sorry, we find the net electrostatic force that would be exerted by a certain source charge at a certain displacement per positive 1 Coulomb test charge. Once you find out what a source would do to every positive 1 Coulomb test charge, then you have in effect, you've in advance found out the general impact that this source charge is having, like on its neighborhood, on the surrounding universe. Like once you know what the source would do to every 1 Coulomb of positive chest charge, then the idea is, well, then from here on in, if I happen at a certain distance, then from now on in, if what I happen to find at that certain distance is 2 Coulombs of test charge, well, I already know in advance that the source charge is doing this many newtons on each 1 Coulomb of positive test charge. So if there happen to be 2 there, I just multiply my pre-known result by 2. If there's 3 Coulombs of test charge, I multiply by 3. In other words, knowing the force per unit test charge is a very powerful, important thing to know about a certain source at a certain location. This thing that we're so from here on in, this is abbreviated not with an F, but with an E. What we're saying is from here on in, E, capital E, is defined to be the net electrostatic force per each unit of positive test charge. Such that whatever this E thing is, right, that I'm defining right now, I'm defining E to be all the information of the electrostatic force divided by whatever the test charge is in that force. So it's all the numbers. It's the numbers of the source. It's the numbers of the distance. It's the numbers of the universal constant. And that's it. It's all the numbers except for or divided by the magnitude of the test charge. So it's like a bundle of numerical information that describes what the impact, what the influence would be of this source at a certain location on any and every 1 unit of charge that could ever be put at a certain location, right? And the whole idea of it is then from here on in, if you know what that bundle of information is, then you just multiply it by the amount of test charge that happens to be sitting there, and boom, you've got the whole force. In other words, finally, like this E. So this whole thing, E, is the package of information that's waiting to generate a force. Waiting for what? Waiting to what? Sorry, it's the package of information waiting to generate a force from some source charge somewhere in the world. This is all the whole bundle of information that's waiting over here at some distant location, waiting to exert a particular force. Waiting for what? Waiting for some test charge to arrive at that location. In other words, this is all of the numbers ready to go, except for the one missing number of what test charge is going to arrive there. If it's 1 unit of test charge, then it's literally all these numbers multiplied by 1. If it happens to be 2 coulombs of test charge that arrive at that location, then two of these whole packages will be exerted, et cetera, et cetera. So it's the force waiting to happen. A force to be a force has to have two objects interacting with each other. This is all the information relating to one of the objects waiting for the second object to come along and actually like actualize it as a force. This capital letter E, this force per charge, is what, as you know, or many of you know, this is called from here on in the electrostatic field. The field is the force waiting to happen. The field is the force per charge. The field is what one object does as opposed to the force, which is what two objects do to each other. I'm going to keep saying that a million different ways. Like the rest of this course is about fields. Okay. Fields and fields are like the everything of physics. I mean, like, don't even get me started. Well, you got me started. Well, this class got me started. I mean, waves are an example of an unthingy thing. Fields are an even deeper or more exciting or more powerful or more blah, 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 something central concept of an unthingy thing. It's all about fields in the end. Let me back up for a second. And you know, you could spend the rest of your life trying to get your mind around fields in a way, or I do, but I'm not trying to intimidate you. I'm trying, if anything, to sort of like excite you, I guess, on a simple level first and foremost, on a direct, concrete, no lie level. What a field is a force per charge. Or, by the way, in the case of gravity, it's a force per mass. All of what I'm saying right now, all retro applies to gravity as well, if that's easier to picture. But what I'm saying on a mathematical level, I'm just looking at the time. Oh, okay, oh yeah, okay. And hold on, bear with me. I'm just changing the screen too. Sorry. Okay. Um, on a mathematical level, fields are not, I don't want them to scare you or stress you or confuse you. On a mathematical level, it's just write this on the board. It's force per charge. In fact, let me be more specific. Well, yeah, let me write that again. On a mathematical level, it's literally what a field is just the answer to exercise 4 of the problem we just solved. It's just like the base level of the force as it would act on any one unit of test charge. And on a mathematical level, we just only care about it or even think about it in the first place because we're just trying to save ourselves time and say, okay, if we can know in advance how much this thing over here is doing to any one unit that might land over there. So let's just track that number in our minds. And then anytime something appears over there that's bigger, we'll just multiply that number appropriately, right? All it is mathematically is the numbers of the force waiting to click in to know what their final multiplier is to become a force. So in other words, again, I'm just saying field by definition is net electrostatic force per charge, specifically oh my God, per test charge per the lowercase q. So in units, for example, in units, the units of electrostatic field are newtons per coulomb. It's like how many newtons of force would you exert on each or per each coulomb that you might be forcing, right? But then let's take it a little more specifically. Like I'm saying the field function, the law, the mathematical function. Oh my God, this is so slow. Notice the function, the mathematical expression, looks exactly the same as the force law, except it's missing one of the q's, right? Because we divide it out by one of the q's. Force is measured in newtons, and it takes two sets of coulombs to make a force. Field is measured in newtons per coulomb because we're dividing out one of the two interacting charges, right? In other words, what I'm saying is, to be a little bit more conceptual, what the field force always is an interaction between two objects. Force is something I do to you and you do to me, right? Like if I'm a proton and you're an electron or whatever, right? Force is something object A does to object B. Field, now we're saying field is something object A just does. Does to what? Well, does to a position in space, if you want to be specific about it. Like, okay, let me say that again. So force is a two object concept. Field is a one object concept. The force is something I do to you if you are at a certain displacement from me. Field is something I just do to that displacement. The field is there at a certain displacement, waiting for you to come along. And the minute you come along to receive the information, then it's a force. So let me be even again more specific for two. Okay. So another way to look at this then is um well, it's just that is that we used to say force is something one object does to another. I mean, and we still say that force is something that one object does to another. But now that we're in the realm of these fundamental forces, gravity and electrostatics, now that we're in the realm of these fundamental forces, now our language and our whole way of looking at it becomes different. Now, when say talk about a proton and electron, or in your mind, like the sun and the earth, same deal, what I'm about to say. We were to a point in history or in our math saying, okay, proton exerts this much electrostatic pull on the electron. Then we sort of realized as a math time-saving technique, but we realized there was maybe a slightly more handy way to say that, which is to say, okay, it's not so much that the proton pulls the electron directly. It's more that the proton creates a pull at every point in space, a pull or a push, whatever. Let me start again. I'm sorry. I mean, this is all right. I'm just trying to be coherent, which apparently is not natural. Let's talk about two protons just to keep the sign simple. We used to say a proton over here would push on a proton that's 5 meters away. Okay. Now, what we say is a proton over here creates a push at every point in space, but particularly the point 5 meters away. A proton creates a push at a location 5 meters away. And then when another proton comes along and lands at that location, it experiences the push and responds. So we now say proton creates field, field exerts force on second proton. Let me say that again. Source charge creates field, field exerts force onto test charge. That's the way we talk about it now. We say that there's a third agent involved. Sound familiar, folks? There's a third agent involved now. It's not just object pulling or pushing other object. It's object creating something between the two objects, and that something, which we call a field, pushes or pulls the second object. We now believe in fields. Now, first, when I first introduced this idea of field like 5 minutes ago, it just was like a mathematically handy device. At first, when you look at field, it's just like a shortcut. It's just force per charge. It's newtons per coulombs instead of newtons. Now I'm starting to sound a little bit more conceptual, maybe. Now I'm starting to like act like this is more than math. I'm saying, wait, when we actually physically picture things from here on in, we actually want to picture the field as playing an actual role in what's going on. It's not just a math shortcut, it turns out. We actually believe that whenever two objects pull or push each other in fundamental ways, that there must be a field in between them mediating that fundamental interaction. Now, let me be specific about that. So I'm getting conceptual now. I'm like, now I just did that exercise I'm not doing any more of the homework right now. I'm just trying to discuss the implications of the homework. Okay. In the few minutes left, let me just so I'm trying to do two things at once. I'm trying to say mathematically, don't let the field throw your game off. Even though everything from here on in we're going to discuss is like about fields much more than about forces. So on the one hand, I just want to emphasize again, mathematically, this doesn't have to be a big stressful deal. The force is Q1 times Q2 times a bunch of other constants. The field is just Q1. Like that is the only difference between the force and the field. Again, like divide force by Q, like by lowercase q, and you have the field. Force is in newtons, field is in newtons per coulomb. Force is what one Q does to the other Q. Field is just what one Q does to a location. But now, conceptually, physically, am I saying that we're supposed to actually like believe that there is like this field thing there actually like meaning something in the physical world? Yes, I am. And that's the interesting part. Like I think it's the truly interesting part. Now, again, what everything I'm about to say now hopefully should not throw off or confuse your calculations. It should hopefully help. But I mean, physics is physics for a reason. I mean, it's not just math, in other words. So let me pause for like 11 minutes and back up and say, like, because this is our new unthingy thing. I'm saying now that there's something in the world called fields that is not made of matter. It is not made of stuff. But it is real scientifically and has an impact on all the stuff of the world that is stuff. So let me tell you why. Like we believe in this. It's not just because it makes the math work. And you may want to write this down. First of all, I'm not saying that every time let me back up again. All forces are interactions between pairs of objects, all forces, right? Now, not all forces have fields associated with them. I am not telling you to go back to Physics 203 now, or your notes from Physics 2 or high school physics. I'm not saying that you should go back now. And whereas you used to think that one surface pushes on another surface with a normal force or with a friction force, I'm not saying now you have to go back and introduce some kind of a friction field or normal field into your thought process. No, not all forces involve fields. The forces that involve fields are these fundamental forces, these forces that seem to occur at a distance. And that's the key to the whole thing. The fact that gravity and the electrostatic force seem to act through empty space without any matter helping the force along, or put another way, the fact that the sun can pull on the earth without touching it, or the fact that a proton can pull on an electron without touching it, is what eventually leads us to have to believe in or recognize something that's going on, which we're not going to call a field. You can call it whatever you want. And when I'm done with this discussion, you can say you don't like it. But hopefully you'll see in the discussion that I'm about to have with the things that I'm about to say, hopefully you'll see that at the end of the day, if you decide not to believe in the field, it's not like you're going to get away with not having to believe in anything. You're going to have to believe in something that that for which the field is actually the simplest possible choice. So here's what I mean. Here's what I mean. Already it's strange enough that the sun can pull on the earth without touching it. Or I think that, or it's certainly interesting. And a proton can pull on an electron without touching it. But now let's be more specific. We've got these equations that tell us exactly the magnitude and the direction with which the sun pulls on the earth, or the proton pulls on the electron, and they work, right? Like they make predictions that turn out to be true. And in fact, in the case of the gravity equation, not only do those equations predict like orbits and eclipses and planetary patterns, but also like they put a man on the moon, well, a few men on the moon, and could put women on the moon, right? Like literally, like those equations work so well that we can build rocket. Well, yeah, okay, but for real, right? So the equations, I'm not saying that they should have been true, and I'm not saying that it makes sense, like that I understand why they needed to be true. I'm just saying they do work and they are true according to the data and the predictions that they produce. So what? Why am I so defensive about the equations? Because now think about these equations. They're very weird. The equations are saying that the amount that the sun pulls on the earth is numerically determined by or numerically dependent on how big the earth is, how big the sun is, and how far away the earth is from the sun. Think about that for a second, or let me think about it with you. So the proton and the electron, it's not just that the proton can pull the electron without touching it. It's that the exact number of newtons that the proton exerts on the electron is exactly determined by, among other things, how far, like what position the electron is in relative to the proton. So what? So this. Think about this. And again, I'm flipping back and forth between the two cases because they're equivalent, whichever one's easier for you to picture in your mind. I'll talk about the sun for a second. The sun pulls on the earth with a certain amount of newtons. We call that gravity, right? So it pulls on the earth. Well, all other things being equal, then the earth starts accelerating towards the sun, right? So now the sun, now the earth, I mean, this is true. Like this is called an orbit and everything. This is why, right? So the sun pulls on the earth, and now the earth is in a new position. It moves. It's like closer to the sun now, or maybe farther away, but whatever. It's closer to the sun now. So the R in the equation is now different, right? So the earth, it got pulled by the sun by an exact certain amount. Now it responded to that pull. Now it's closer to the sun. Now the R is different in the equation. So now evidently, and apparently according to the data, now the sun adjusts its pull and reaches out and grabs the earth with a new freshly calculated number of newtons. And then this keeps going on and on and on, right? Or same thing with the proton and electron. What am I trying to say? I'm trying to say, wait a second. Evidently, every time an electron moves somewhere in the world, a proton knows that it did. Apparently, the proton somehow learns of the new location of the electron. And why do I believe that? Or how do I know? Because the proton evidently adjusts its pull accordingly. Like, and if you trace the orbits of these objects or trace the trajectories or take a bunch of data, you see that that's what's going on. So the excitement is, it's not just that the sun can affect the earth without touching, or that a proton can affect an electron without touching. It's that specifically the information of the electron's size and whereabouts are somehow always accessible to any and all protons everywhere else. Like, protons over here know specifically how big electrons are over here and exactly where they are. And when they move, the proton finds out through empty space. Now, when I say, and you could tell, I can't fake this, right? This blows my mind every time I think about it. And I'm not lying to you. I'm not trying to trick you. I'm trying to show you how sort of tricky and interesting the universe is. And this is like and Newton was flabbergasted by this, and Einstein was flabbergasted. Like, I'm not saying we don't have increasingly precise new ways of understanding all this, but the fundamental thing of action at a distance is that it's inescapable. If it all works like this, if these equations actually are correct, or even if they're not perfectly correct, if they're somehow usable enough to be making accurate predictions, then what it seems to imply about the universe is that stuff over here knows the vital stats of stuff over here, even when the two stuffs are not touching each other or sending any kind of material objects to each other in order to convey this information. And the information apparently is updated continuously all the time through all of space. So if the electron over here, or excuse me, the proton over here knows how big the electrons are over there and where they are, I don't mean know like consciously. I'm not trying to mess with you. I don't mean like know like it could write out a document or like go to a therapist about the knowledge. I don't mean that. I just mean the information of the electron is over here at this point in empty space is accessible continually and updated continually to the proton over here at this other location separated by empty space. So somehow the information, the numbers, the vectors, the numbers are getting transmitted back and forth through empty space all the time. And I mean empty space. I mean, there doesn't even have to be air there. Apparently, like, right, because the universe holds itself together even in outer space where there's no atmosphere, right? So something is in the space containing the information. Do I really know what that something is? Of course not. Like, and again, why am I excited about this every time, every year? Because it is still mysterious and intriguing to all people who think about it. But I have some grip on it. I have a name for it. I call that the field. That doesn't answer all my questions, and it doesn't make all the questions go away, but it also doesn't, right? It doesn't. But it also isn't a lie. I'm just saying there's something that is holding the information. So bottom line, what is a field? Because I know it's 419. What is a field? Field is our name, our word for the presence of information, specifically vector information, magnitudes and directions of forces waiting to happen. The field is the vector that is sitting at every point in space the minute one source charge comes along into the universe. If a source charge comes along, it places a vector of a certain magnitude and a certain direction at every single point in space. And that vector represents the amount of force, the number of newtons that will be exerted on any one coulomb of test charge that could come along to that point in space. And I know it's 420. Do I literally believe there's like chalk arrows in space? Of course not. When I say there's a vector everywhere in space, again, that's just a word. That's just a representation for the information that must be everywhere in space. And if we use vectors and we use field lines and equations, then I'm not saying that's literally the way God looks at it, but I'm saying that's the way we look at it so that we can make accurate predictions. The vectors, the arrows, the numbers, the equations are all metaphors in our minds to help us make predictions and make sense of this inescapable reality that what is going on over here in space is known to what is going on over there in space. What's in between holding and transmitting that information is called a field in physics. Okay, you've been very patient. Well, obviously we'll keep going with this next week, but carry on. Like keep doing your homework, whatever. I'm here for a couple minutes if there's any questions, but that's it. Thank you for indulging me. Have a nice weekend. Yes, I'm stopping the recording, but I'm here.